A conducting rod of length capital L is moving in a magnetic field region where the magnetic field is uniform and it's perpendicular to the velocity vector of the rod. The speed of the rod is also given. So the rod is moving in the plane of the page, and the magnetic field is perpendicular to the plane of the page, and it's pointing into the page. What is the potential difference between the two ends of the rod? Here we can directly apply the formula that we derived earlier. The induced EMF between the two ends of the rod is equal to V times B times L. We just plug in the numbers and we get the EMF, or the potential difference between points A and B, equal to 0.60 volts. Now, what is the direction of the induced EMF? In other words, which point is at a higher potential? Let's think about the direction of the force acting on a positively charged particle in the rod. Now we need to do V cross B. Align your right hand in the direction of V, pointing towards the lower right corner, and then curl your fingers in the direction of the magnetic field, which is into the page. Your thumb is pointing towards point B. So that will be the direction of the magnetic force acting a positively charged particle. On the other hand, the negatively charged particles, like electrons, would experience a force in the opposite direction. So the force on negatively charged particles will be towards point A. Because negatively charged particles are the ones that are actually able to move, usually, we can expect that there will be some excess negative charge at point A and excess positive charge at point B. So point B will be at a higher potential. Negative charges will move towards point A, and point A will be negatively charged. Point B will be positively charged, and therefore point B will be at a higher potential value. The next question is, once the moving charges have reached an equilibrium, now that we have an excess amount of electrons at point A and the deficit of electrons at point B, what is the magnitude and direction of the electric field in the rod? Now we have already determined that point B is at a higher potential and point A is a lower potential, and electric field vector points from high potential towards the low potential point. So electric field vector points from B to A. How about the magnitude of the electric field? To find the magnitude of the electric field, we can just divide the potential difference by the distance between points A and B, which is the length of the rod, and the potential difference is equal to the induced EMF. So we divide 0.60 volts by 0.26 meters, and we get 2.3 volts per meter for the magnitude of the electric field vector. If the rod moved parallel to AB, meaning if the velocity vector pointed from A to B or from B to A, in that case, if you do V cross B, then the magnetic force on a positively charged particle would be, or a negatively charged particle, doesn't matter either way, then the magnetic force on charged particles would be directed perpendicular to the rod. In that case, we can't get any potential difference between the points, between the ends of the rod. What if the rod was moving out of the page or into the page in that direction? In that case, V cross B would be 0, because V would be either parallel to B or anti-parallel to B. Both will result in the cross product being equal to 0. In that case, we wouldn't have any magnetic force acting on the charged particles. So again, there will be no potential difference forming between the ends of the rod.